Okay, so review 4.1 through 4.4. Go quickly. No displacement, and amplitude, and frequency. No, they're units as well. Period, and phase difference. And then make sure you're familiar with that equation on the acceleration is equal to negative omega squared x. A max equaled omega squared a, where a is the amplitude. And why is there a negative there? The negative indicates that classic definition of harmonic motion, that it was proportional to but opposite in direction. Remember Hooke's law? F equals negative kx? Well, think about that. If you stretch a spring, it pulls back. If you compress a spring, it pushes back. So basically the force of the spring is always in opposition to the force that you're applying. Sort of that same concept. So pretty simple to understand there, I think, anyway. So going forward, know those equations. What were those equations? I got my book here. Let's look here. They're on page 198. Those equations that describe simple harmonic motion. Usually the phase angle is 0, but the big equation you want to come out of there that's very common to be used a lot is 2 pi over omega. Remember, omega is in radians per second and is an angular frequency. So that'll help you out. Omega, right? And so make sure you pull that information from there and look over those equations and make sure you're familiar with them. Phase differences, that phase angle, you probably just want to know a concept there. So if you had to move this forward and show what it looks like with a fourth forward, so that means that if it was displaced or had a 1/4, so that means that the wave is now going to come in basically here. So it would look something like that, be displaced, a fourth of a wave forward, a half a wave forward, then you would come in right there, right? So I'm going to erase that so it doesn't confuse you. All right. So going forward, we're 2.5 minutes in. Let's see, a couple other things that we can add to here. If we want to know the velocity at the amplitude, the velocity, the maximum velocity equals omega a. But if you want to know the velocity anywhere, so let's say if you know a, and then if you want to know the velocity right there at point P, for instance, then you would have velocity at any point along there would be omega times a squared minus x squared, where x is that distance from the midpoint line to P. Okay? And that's the square root of that, the square root of a squared minus x squared. And that'll give you the velocity anywhere. And so there's that basic idea. Energy in simple harmonic motion. Energy. So if you plotted potential energy, you pull a spring, and when you pull a spring, it's got maximum energy. Remember, that's 1/2 k x squared u of a spring, and that would look something like that. We got to see that quite common. So that's u, and of course, then therefore, going and grabbing a color. That would be, I know it's not symmetrical, but that would be kinetic energy. And then grabbing another color, and that would be total energy. So T, E, U, and E, K are defined there. And when we talk about the energy in simple harmonic motion, then we can do 1/2, let's do mv squared. But if you recall, V is equal to omega a. So if you substitute in that, you get EK at, and where would EK be at its maximum? It would be at 1/2 m omega squared a squared. Is that right? I think so. And so that's where you know that and that actually could equal its total energy, couldn't it, if you're at A? But what if you weren't at A? Then you'd have to do x squared EK equals 1/2 m times x initial squared minus x squared, and that would give you the kinetic energy somewhere in there. Going forward, what if you wanted to know the potential energy somewhere? So if you did EP equals 1/2 m omega squared x squared, and that's if you want to know, like, at some point along here, just at some point, so not at different. So, but the key thing that you can always figure out is you could always figure out the maximum energy right there, and you know what the total energy, and you know the total energy remains constant in something undergoing simple harmonic motion. Make sure you know what damping is. Let's write that down. Damping, D-A-M-P-I-N-G. Gave you some examples of that in class. Make sure you understand that it involves a force and that's opposing the motion of harmonic motion. It sort of takes away the energy of the object in simple harmonic motion. Give me some examples of it. I gave you some examples in class. Critical damping, underdamping, overdamping. Anyway, try to do it. Make sure you know what damping is. Let's see, what else do we need to know? Force vibrations and resonance. Gave you examples. Showed you an example of resonance and did a demonstration for you. Make sure you've looked through that and understand the concept of resonance. Wave characteristics. We have traveling waves. Look those up. Make sure you get those. Standing waves. So make sure you get those done. And know that, let's see, wave speed, velocity of a wave is equal to frequency times wavelength. Nice equation to pull from there. And I'm going to pause for a second here. Longitudinal and transverse. I'm going to let you look those up so that you know. Remember, this is sound. This is your electromagnetic, E&M, electromagnetic, and sound. But you need to know what they are like. I want you to know which one is perpendicular to the direction of wave travel as opposed to parallel, the energy, how it oscillates back and forth. Let's see, you should know those graphs that we did. You've had a couple problems with these, with graphs of displacement time. So displacement versus time, and just erasing a little bit right there, coming back, and then the displacement position. So displacement position. So, and you've had examples of both of these. So you have a wave traveling along here. What can you get from here? Well, you can get the period from this wave on the wave pattern on the left, and you could also get the amplitude as well. And from the one on the right, you could get the wavelength, definitely. So the combination of the two, you can figure out the wave speed. So make sure to be able to extract information from graphs. Make sure and look over that. Then we're on to wave properties. Reflection, refraction, and let's see. I think that's sort of the basics that I want there. Oh, and diffraction. Want to make sure we know those three. Snell's law. Make sure you understand that concept. We should be getting pretty good with that. What else do we want to know about waves? Constructive, and I'll leave it short. This is for my class, not anybody else in the world. Destructive, and know the difference in those two and how they occur. And apply that principle of superposition. Position, to know whether you're getting constructive or destructive interference taking place. All right, a couple last basic equations that I just wanted to make sure that you were aware of. Velocity of a wave on a string is equal to the square root of the period over mu. If you recall, mu is mass per unit length. I won't put it there. I'm going to put it down here. Mu equals mass per unit length. So as long as they just kept on adding length to the rope, if they made it longer, nothing's going to happen. The mass per unit length is going to stay the same because the mass will increase proportionally. And don't forget about the concepts of that wave path. Remember those points of no movement, nodes, And if you had a standing wave between a wall and a wall, I guess, for instance, those would be considered nodes. So there'd be 1, 2, 3, 4, 5, 6 nodes on here. And then these were called the antinodes, the points of maximum displacement. And don't forget that concept of rarefaction and compression. I'm just sticking stuff in here now. Rarefaction and compression in that longitudinal sound wave. Areas of high pressure in a compression and low pressure in a rarefaction. And let's see. Don't forget just the classic, always never forget just the velocity is equal to the change in displacement over the change in time. You can always use something like that because it's used in a derivation of Snell's law when they define the time as it moves into a new barrier. What about when a wave hits a new medium, the reflection? How does it reflect? When it hits. Not a good drawing there. I'm at 11 minutes now, so I'm going to stop here very quickly. But remember, if we had a wave pulse come down like that and hit this wall and reflect, then the pulse coming back in a new color, I'll wrap it up with this, would of course come back. If that was a brick wall and it's more dense, it would come back like that. So it would reflect back that direction. So that is basically it. So here's the wave coming down this way, hitting the wall, and then reflecting back. I know that's not symmetrical in that case, but it would be if there was no loss to friction. Okay? All right, that's it for this. So we're going to stop at 11 minutes. That's all of Topic 4. No, I shouldn't say that. That is not all of Topic 4. It's your job to go through the book and make sure you pull out all the basic information. Okay?